Hello everyone, my name is Patrick Flynn, and in this presentation I will be presenting the A2 paper, which is on analog malicious hardware. So let's start with an introduction. So hardware is the key to security, and this probably goes without saying because hardware is the base to every computer system. It is the base on which our entire software stack runs on. Because it is the core of every system, any bug in the hardware system will impact the system as a whole. And bugs can be malicious or they could be simple bugs. Simple bugs in hardware are not unheard of. A famous example of this includes the Pentium floating point division bug back in the 1990s. But bugs in the hardware can also lead to very malicious results. And a famous example of this was the recently discovered meltdown in Spectre bugs, which is an exploit based on the speculative execution abilities of modern hardware, predominantly in x86. And the problem with hardware flaws is that they're often undetectable by the software. Software will run on them, and most of the time, if there's like a serious bug that affects the output, they'll be detected in manufacture. But if it's a more subtle bug, it often requires digging to see it, but when it is found, it can lead to very bad results. Most of us are familiar with these hardware flaws. As mentioned, they're not unheard of. But a lot of us are less familiar with directed hardware attacks. And that is what we'll be discussing in this paper. So, some background. Very few chip companies today manufacture their own chips. Unlike most industries where the company will have its own factory, in the case of the chip industry, manufacturing chips is very difficult and very expensive. Early on in the chip industry, most companies would do this, and today there are a few that still do, Intel, Samsung, and Texas Instruments being the big examples, but most chip companies today have moved on to the foundry model, including very big players in the industry like AMD, NVIDIA, and Qualcomm. And the foundry model is basically where the actual manufacturing of chips is outsourced to a different company. So a company will just design the chip and eventually lower that design to a very low level, and then a foundry with all the complicated and sensitive manufacturing equipment will manufacture the chip and then deliver it back to the design house. So obviously there are huge pluses with this model, which is why it's taken off. Unlike many other industries, semiconductor fabrication is very expensive and very difficult. The equipment needed to do it is extremely specialized and extremely sensitive, and as it goes with equipment like that, it's just very expensive. And this fabrication technology, like all technology, improves over the years. As time goes on, we've been able to make chips smaller and smaller, and as a result of that, we've been able to put more and more design into a smaller and smaller space. And as time goes on, this will only improve. And upgrading to this hardware every few years is very expensive. Only huge companies like Intel and Samsung that produce so many chips that they're able to carry and offset the cost and still make a profit are able to do this. On the flip side, designing hardware is very cheap. This is something anyone can do. All you need is VHDL and a simulator to run this, and you're good to go. So this model is a huge win for everyone. But there's also some major minuses with this. Only a few companies are able to do this. The biggest one being TSMC, Taiwan's semiconductor manufacturing. In addition to that, they're located internationally. So this has the potential to create huge issues with the supply chain, as we saw during COVID. If even one of these companies has any issues or were to just disappear or whatever, that would have a disastrous effect on the chip industry. And then on top of that, these companies are generally located in foreign countries. For chip designers in the US or some other countries, this may not be a huge issue, but for chip designers in other countries, outsourcing the manufacture of the chip could be a big security issue. And then on top of that, there's the practicality that 2 of the 3 biggest chip manufacturing companies are located in one of the most politically contentious places in the world. So, an example of a malicious hardware flaw that we don't often think of is a hardware Trojan. And Trojans, you're probably familiar with the software Trojan, which is basically extra logic added to a program for a nefarious purpose. Usually it exploits a vulnerability and is meant to give an attacker a backdoor later on to do whatever it is they want to do. And believe it or not, hardware Trojans are actually a thing. You can actually add a Trojan to hardware. And this would usually be extra logic that monitors a certain part of a circuit. And if this Trojan is triggered, it will exploit a vulnerability in the hardware and allow an attacker to do something later on. These Trojans are difficult to detect. They're quite difficult to implement, but it's certainly not impossible, especially in this world where most hardware is just sent off somewhere else to be manufactured. Most Trojans are digital-based, and just as some quick context, all circuits are fundamentally analog, which means that they're built out of transistors and capacitors and simple analog circuits. But computer logic is digital, meaning it's based on ones and zeros and follows the laws of digital logic. And most Trojans are digital based for the simple reason that hardware designs start digitally, and adding digital logic to a digital circuit is very easy. However, if you go the path of an analog Trojan that doesn't rely on the overhead of digital logic, you can potentially make this much smaller and much stealthier. This analog circuitry requires less electronics to implement, and because it is so much smaller, they're harder to detect. All right. With that in mind, let's take kind of a deeper dive into these Trojans. So we briefly talked about the foundry model, but let's go a little deeper into the chip design process. The chip design process starts with just the high-level design, which many of us are familiar with, VHDL and Verilog, and maybe some software-based simulators and stuff like that. After a Verilog design is finalized, then this will go through steps such as logic verification and logic synthesis, and sometimes this is done with FPGAs, and the purpose of this is to validate the logic and make sure that this is something that can be run on actual hardware. In other words, be expressed with actual hardware circuits. After this hardware design is lowered down to the electrical circuitry required, and then this electrical circuitry is designed and placed in such a way that it can be manufactured onto a small chip. And this is known as the back-end design phase. This can be done by a chip manufacturer or it can be done by another third party. But this will create the final design that is fabricated. This final design, this layout is then sent to a foundry where the equipment will create the physical chip. This chip is then sent back to the original design house for verification, and verification is where you just give it the instructions, all kinds of expected input, make sure you get the expected output, and if this passes, it's packaged and sent to customers. So in this paper, the attacks are implemented, or attacks can be implemented in either the back-end phase or the fabrication phase. In this paper, we will assume that they'll be in the fabrication phase. And the fabrication phase is what we would assume to be untrusted, since this part is done solely by a third party. All the other parts can be done in-house, but this part is done by an untrusted third party. So, what is a hardware attack? So, hardware attacks, and really any attack for that matter, they have two parts, the trigger and the payload. And the trigger is the mechanism that will release the payload. The payload is just the malicious actions that we take to allow an attacker to either do something or get control of the system. Now, the trigger is important in hardware, in any situation, but hardware especially. We want to make sure it is hidden from analysis. We want to make sure it's hidden from the final chip verification stage. So we don't want it to be triggered by accident when we're feeding inputs or checking the electronic behavior or whatever the case may be. So how do we implement this? So there's a couple of ways to implement these triggers. The easiest way would be a single stage trigger, which would basically monitor a certain part of the circuit, and if a certain condition is met, then it is triggered and the payload is released. It's very easy to implement, but it could potentially be easy to toggle since there's fewer protections. You end up with a single point of failure in this method. The other solution to this would be a multi-stage trigger, which means that there's multiple things that have to happen in order for the payload to be released. This is harder to implement. It requires more circuitry and more things to work, but it is potentially easier to hide from the verification stage later on. So how do these triggers work? Excuse me. So hardware Trojans, at the most basic level, they maintain a counter, and if the condition of this counter is met, then the payload is triggered. This counter is a little more complex than something like if it's hit like 5 times, then triggered. There's usually a timing component to it, but at a fundamental level, timing is everything. You want to make the condition in such a way that it's possible for it to be hit, but not too easy. And as we mentioned earlier, hardware Trojans are often done digitally, just since the original design is done with digital logic, and digital counter certainly exists, but this requires a lot of extra circuitry. And as we'll discuss later on, having a lot of extra circuitry makes the Trojan potentially easier to detect. Analog Trojans use capacitors, and capacitors store energy. They can be progressively stored with more and more energy, but they also leak energy. So this means that if a capacitor is not filled within a certain period of time, it will leak the energy back, which effectively makes it function as a counter. And when they're fully filled, they can go on to trigger the payload. So you get the best of both worlds with basically one electronic component. So what is the payload in a hardware Trojan? So since it is hardware, and since our goal is to keep it hidden, but the payload is limited. Typically, a payload would be something like flipping a reserve bit, like a system bit, to allow software to gain more access to the system. So, for example, when you have a CPU running an operating system, there's different privilege modes. One privilege mode allows access to things like interrupt the hardware, much more control over the underlying security. And then you have user mode, which is like a very limited mode that requires the privileged OS in order to run. A hardware Trojan would allow regular user mode software to change the hardware bits that are set to keep user mode software from accessing privileged instructions. Alright, so with all that background, how exactly do we implement this thing? So in this paper, the authors tested this on a real chip. They fabricated a real chip. The base of this chip was the OpenRISC 1200 CPU, and the goal of the exploit is to set the SR register, and the SR register contains the privileged bits that we talked about in the previous slide. Now, for identifying the attack on this particular CPU, again, we want this to be hard to trigger. And by hard to trigger, we don't necessarily mean just chip verification. We also don't want programs running on it to accidentally trigger it. And by this is what we mean by the compiler accidentally triggering it. We don't want like a common sequence of instructions generated by a compiler and just running as a normal program to trigger this. So to determine this, the authors used a popular suite of benchmarks for an embedded system, and they also analyzed an OpenRISC core written in Verilog. And the result of this attack was around 3% of the wires were significantly underutilized, and one of these sets of wires was the divide by zero circuitry. And if a divide by zero exception occurs, it will simply set a hardware flag. And this particular set of the circuitry is useful in that it's highly unlikely that a regular embedded program, or any program of that matter, would be continually dividing by zeros in a short period of time and trigger the exploit. So in the chip that the authors implemented, they added two analog circuits. One had the single stage trigger, the other had the multi-stage trigger, and they used 65 nanometer CMOS technology to test this. So in terms of implementing the attack as they fabricated the hardware, the overall process of doing this is you want to first locate your inputs and outputs. As we mentioned earlier, this was being done in the fabrication stage. So after you've determined what part of the hardware you want to attack, you have to find some empty space within the circuit layout and then insert your malicious circuit there. They also cut the reset wire for better control over this, and then you have to route the attack circuit to the payload circuit, which in this case would just be routing the wire to the SR register in such a way that it would flip the bit. Now, a big question is, can we detect this malicious circuit? So on an analog attack, power fluctuations are extremely minimal, and in order for the attack to be detected, it would require certain rare events to occur. The digital version is a lot easier to detect this because there's more gates and therefore more power being used, so events that could lead to this detection happen more frequently. Alright, so with the chip implemented, we of course want to evaluate it and see how it performs. So what did the setup look like? The authors implemented both attacks in the processor just since fabrication is expensive and difficult. They connected the chip to another PC so they could evaluate it and control it easily. They used a programmable clock so they could control frequencies and see if or how that affected it. And then they also placed the chip in a temperature chamber. And this is important because circuits react to different temperatures in different ways. So this is obviously something worth measuring. In terms of the software, they attacked it in two ways. The first way is through kind of a conventional user mode attack, which was to run Linux and then run a user program and see if the attack could be triggered from just regular user mode code. And then they also did some more targeted attacks to examine how the circuit itself behaved. So a few interesting results. Obviously, running the software in the design way was able to trigger the attack, but there was also a few other interesting results found. Temperature is very important to the performance, to how the attack performs. A higher temperature means that more cycles are needed to trigger the attack, just because of how the capacitor reacts to these higher temperatures. And then in terms of how long the circuit stays toggled, higher temperature also means that the circuit is toggled for less time. And then to go back earlier to what we said about the compiler triggering the attack through like common sequences of code, they ran the benchmarks again on their circuit, and they found that they were not able to trigger it through just normal running of normal programs. All right, with the evaluation, where do we go with what we formed here? So the big question is, can this attack be scaled to more complex systems? OpenRISC is complex enough to run Linux, and it has a complexity similar to mid-level ARM chips, but OpenRISC is obviously not really used in the real world. So the big question is, can it be run on the complex chips used in the real world, like x86? And they believe that the answer is definitely yes, because of the simplicity of the attack and then the significantly greater complexity of x86. And then the big question is, how do we defend against this? Existing defenses do not work. Side channel analysis doesn't detect it. Is because such a limited amount of circuitry is used, visually looking at the chip is extremely unlikely to detect it. And then it's just unlikely to be triggered in the post-fabrication testing because the trigger is just too specific. But how do we defend against this? The ideal way to defend against this is a new testing paradigm needs to be implemented, and instead of just giving the chip input and checking if the output is correct, a more comprehensive test that looks at the chip at the whole, like what are the registers doing, and seeing how the environment as a whole responds to a certain input would be the best defense against this. Another possible solution is split manufacturing, which is where you have different parts of the chip manufactured at different places, but this could have downfalls. It is still possible to add attacks if you can figure out what the logic is on the other part of the chip that you don't have. So in conclusion, hardware attacks are certainly possible. You can do them in the fabrication stage, and it is certainly possible to make them very stealthy and hard to detect. And as the authors demonstrated, they do work. They can be implemented, and they can be implemented relatively easily and hidden successfully. So thank you very much, and this concludes my presentation.